Let's look at how mass plays into this moles amount of chemical. We looked at the very first that we have count and we have mass and we have volume. Now, from the last slides, we saw that count is impossible. It's just too big of a number to count out all the atoms in anything or all the molecules in anything. So count we still use because we know the count of things. So we know that 6.02 times 10 to the 23rd equals 1 mole. So this count, the 6.02 times 10 to the 23rd, is a mole's worth. The number itself, we give it a name. We call it Avogadro's number. It was named after Avogadro. Avogadro didn't come up with the number. He maybe came up with the idea. And then in modern times, as we got better equipment, we were able to come up with the actual number, the 6.02 times 10 to the 23rd. And then the number was credited to Avogadro. So Avogadro was a chemist who lived back in the day and was working on things with chemicals, but never had the equipment to come up with the number with the modern precision. So when they found it with the modern precision, it was credited to his name. So we call it Avogadro's number, 6.02 times 10 to the 23rd. So where did this number come from? Why is it such kind of a random number? Why didn't we just use 1 times 10 to the 23rd? Why is it 6.02 times 10 to the 23rd? There must be something kind of unique about that number that helps us out. So let's see what that is. So let's look at a carbon atom. And if I have a carbon atom and I have carbon 12, it'll weigh 12 AMUs, atomic mass units. An atomic mass unit is really, really small. I can't put that on a scale and weigh that. So one carbon weighing 12 AMUs is not really a useful weight system because it's so incredibly small to weigh out a single carbon atom. That's not going to work out very well. But then the question would be, let's go to something bigger. Let's go to 12 grams. 12 grams is something I could weigh out. And let's use 12 for carbon because we already use 12 for the AMUs. So using 12 grams instead of 12 AMUs would be a lot easier to weigh on a scale, something that we could do. So if we want 12 grams of carbon atoms, we are going to need a lot of them. So we're going to have to start piling carbon onto the scale until we get to 12 grams. The question becomes, how many carbons should you put on the scale if you want to get 12 grams? And the amount that you're going to have to put on the scale to get to 12 grams turns out to be 6.02 times 10 to the 23rd carbons. So if I put 1 carbon on the scale, it's going to weigh 12 AMUs. If I put 6.02 times 10 to the 23rd carbons on the scale, it's going to weigh 12 grams. So chemists were smart in the idea of keeping the number the same, but the units change. So if we put 1 carbon, it's 12 AMUs. If we put 6.02 times 10 to the 23rd carbons, it's going to weigh 12 grams. So number-wise, we don't have to deal with new numbers for everything. We can just look at the periodic table and say, what does that atom weigh? What's its atomic mass? And then if we have a 6.02 times 10 to the 23rd, or a mole's worth of that, that's what we'll weigh in grams. So it's an easy way to figure out how to get a certain amount of chemical because counting is impossible. So now what I can do is say, I would like a mole's worth of carbon atoms. Then I know, okay, just go to a scale and weigh out 12 grams. I don't have to do any counting. It would take me lifetimes to try and count that all out. But putting 12 grams on a scale takes seconds. I just open it up, start scooping it on until it reads 12 grams, and I'll have a mole's worth. Now, how accurate it is, obviously it depends on the scale. Will I hit it exactly to the atom? Probably not, but I can get close enough that it's going to be useful for my work in the lab. So doing it by mass is much, much faster since I have such a high count. Let's do this with another atom. Let's do oxygen. So if I have 1 oxygen atom, I'm going to look at the periodic table and see what is the atomic mass on oxygen. I'm just going to round this one. In this case, since it's so close to 16, I'm just going to say it's 16 AMUs. So one oxygen atom weighs 16 AMUs, meaning if I had 6.02 times 10 to the 23rd oxygens, it would weigh 16 grams. So same number once again is in play and is in use. But since an oxygen atom is bigger, when I have the same count, I actually have more. It's kind of like saying cherries versus, oranges. If I have a dozen cherries, that's not going to weigh very much because a cherry by itself doesn't weigh that much. If I have a dozen oranges is going to weigh a lot more because an orange by itself also weighs a lot more than a cherry does. So keep in mind, when we have a count of things like 6.02 times 10 to the 23rd, it doesn't have one set mass. It really depends on what is the thing, the atom that you're looking at. Is it a big atom? If it's a big atom, then having 6.02 times 10 to the 23rd will give you a big mass. So there isn't a fixed mass for a mole's worth of anything. It just depends on how big the atom is that you're dealing with. So this idea of what it takes to make what a mole's worth is of an atom has a name. It's called the gram atomic mass. That's going to equal the mass of 1 mole of atoms. So we use gram atomic mass. We abbreviate it GAM. And we can only use it for single atom things. So we can just say carbon atoms, oxygen atoms, helium atoms. We can't use it for molecules. We can't use it for ionic things. That's going to have a different term for it. So let's look at how that works for molecules. Let's do that with water, H2O. So H2O is 2 hydrogens plus 1 oxygen. And let's say I have 1 mole of water. So I have 6.02 times 10 to the 23rd water molecules. And I wanted to know what that would weigh. Well, I can't look up water on the periodic table because that doesn't exist. It's made out of 3 atoms here. So if I have a mole's worth of water, I'm going to have a lot of atoms. I'm actually going to have 3 atoms per every molecule. So when I break this all up, if I have a mole's worth of water, I'm going to have 1 mole of hydrogen. I'm going to have another mole of hydrogen and 1 mole of oxygen. So 1 mole of water molecules, if I break it apart, is going to come with a mole's worth of hydrogens, another mole worth of hydrogen for the other H, and a mole's worth of oxygens. For an analogy, you could think of it like bikes. If I have a dozen bikes or bicycles, I have a dozen rear wheels, I have a dozen front wheels, and I have a dozen bike frames. So when we have an H, and an O, we're kind of treating it like rear wheels, front wheels, and frames, because I have 3 parts that make up a water. So when I break a mole's worth of waters down, I get a mole's worth of H's, a mole's worth of H's, and a mole's worth of O's. And we know the weights on these. So if I want to know what a mole's worth of hydrogen weighs, I can just look that up on the periodic table, and 1.008 grams. Pretty close to 1 gram. This mole of hydrogen is also 1.008 grams. Moles worth of oxygen, I'm going to call it 16 grams. So this is what all the individual parts weigh. So if I add this up, Going to get 18. We'll just leave it at 18 grams. So a mole's worth of water weighs about 18 grams, a little extra. And that's going to be 1 mole of H2O, which, remember, is 6.02 times 10 to the 23rd water molecules. Now, when it comes to how many atoms, there's going to be more atoms than there are molecules. So if I have that many water molecules, how many atoms do I have? Well, I'm going to have 3 times as many because every molecule is going to come with 3 atoms. So I could just take it and multiply 3 times 6.02 times 10 to the 23rd. And that'll give me 18.06 times 10 to the 23rd atoms. So we're starting to see a little discrepancy here between what counts as a count for a molecule and a count for the atoms. Since every molecule has 3 atoms in it, we would have to times by this if we wanted to know how many atoms. If we just wanted to get a mole's worth of water, go over to a scale, pour 18 grams on it, and put it in a cup, and you have a mole's worth of water molecules. But you do have a lot more atoms because there are 3 atoms in these each of these water molecules. So we give this its own special name, this what does a molecule weigh? And so we call it the gram because we're measuring in grams, and it is the molecular mass. Abbreviation GMM. And it is going to be the mass of 1 mole of molecules. So we would say the gram molecular mass of water is 18 grams. That is what 1 mole's worth of water would weigh. So we have gram atomic mass, gram molecular mass, and then let's see what we're going to do for ionic things. Fairly similar. Let's look at 1 mole of salt, or sodium chloride. So if I have a mole of sodium chloride and I break that apart, that means I'm going to have 1 mole of Na and 1 mole of Cl. For a mole of Na, I'm just going to look it up on the periodic table like anything, and it's about 23 grams. And then I'm going to look up chlorine on the periodic table, and 35.45. Since salt comes as those 2 pieces combined, I'm just going to add those 2 together, and it looks like we're going to get 58.4 grams. And that's going to equal 1 mole of NaCl. So if I want a mole's worth of salt, I'll take it to the scale, start pouring salts until I read 58.4 grams, and then I'll have a mole's worth of salt. We can't call this gram molecular mass because this isn't a molecule, this is an ionic compound, so it has its own name as well, and we call it the gram formula mass. Or GFM. It's the mass of 1 mole of an ionic compound. So GAM, gram atomic mass for atomic things, gram molecular mass for molecular things, gram formula mass for ionic things. Let's try one that's a little bit tougher. Let's look at ammonium carbonate. So NH4, and we'll need 2 of them with carbonate CO3. Keep in mind it's balanced charge, it's ionic. We have ammonium that's +1, carbonate that's -2. We need 2 ammoniums for the +2 to match the -2. And the question then becomes, what does a mole's worth of that weigh? And there's a lot more going on. There's a lot more atoms involved. This is probably going to be something that weighs a lot because an individual molecule or a formula unit of this weighs a pretty good amount. So I have to go through and figure out the weights piece by piece by piece. I even have a parenthesis in here with a 2, which means I have 2 of this group NH4, which means this has 2 nitrogens in it. It has 8 hydrogens in it, 1 carbon, and 3 oxygens. So this ionic compound is made out of 14 atoms, 2 of them nitrogen, 8 of them hydrogen, 1 carbon, 3 of them being oxygen. So whenever we have a parentheses, you can kind of think like foiling in math class that you're going to multiply it in. I have H4 twice, so I must have 8 H's because I have 4 of them twice. And then I have 1 nitrogen, but I have this group twice, so I have 2 of them. The other way to look at it, if that doesn't make sense, is just to think, okay, you have NH4 twice. So NH4 twice is 2 nitrogens, 8 hydrogens. All right, I have nitrogen, and I know a mole's worth of nitrogen, if I look at the periodic table, weighs about 14. So 1 mole of nitrogen weighs 14. I have 2 moles of it, though, and that's going to be 28 grams. As far as hydrogen goes, hydrogen on the periodic table is 1. I have 8 of them, and that's going to be 8 grams. Carbon on the periodic table, we're going to go with 12. And I only have 1 of them, that's why I have 12. Oxygen on the periodic table, 16. I have 3 of them, so 48 grams. I'm going to add it all up and get 96 grams. And 96 grams is 1 mole of ammonium carbonate. So when you have something that's a little bit bigger with some parentheses, you just have to be careful to make sure you pick up every atom in there and then figure out the weights on all of them. You're pretty much just going to use the periodic table to figure out the weights. If it's really, really close to a whole number, we can round to a whole number. If it is a decimal, like a 0.3 or 0.4, we will use the decimals. We don't always round. Just if it's really, really close, do we round. But if it's in the middle, 0.5s and things like that, we're not going to round them. So that is how we figure out the molar mass of different compounds.